Right, we want to answer some of the questions here in regards with electromagnetism. So the first question I have here: illustrate by sketch the magnetic field variations for the diagrams below 1, 2, and 3, and also describe also the magnetic fields produced by permanent magnets and electromagnets. We've already explained that in the lessons, and the lessons are very explanatory, really. Have gone into details. Number 3, the flux flowing through a horseshoe magnet is 0.3 Weber, so that's phi. The cross-sectional area of the gap is 150 millimeters squared, so straight away you need to convert. This is area, or A, is 150 millimeters squared. You have to convert this to meters squared, so that is 150 times 10 to the power of minus 6, not minus 3, because it's millimeters squared, not millimeter. And calculate the flux density in the gap. It's very simple. The formula for that is B equals phi over A. B is 0.3 over 150 times 10 to the power of minus 6. You do that calculation. B is, or flux density is 2000 Tesla. Next question. A coil used in a radio circuit acting as a filter or suspense suppressor is wound on a toroid core, 30 millimeter mean diameter. So that means you need to find the area. It's given you the mean diameter. That means straight away you need to convert it to meter first of all. That's 0.03 meter. And if you times that by pi, then you find the mean circumference, which is the length of the magnetic field, or the magnetic circuit, sorry, the length of the magnetic circuit. There are 40 turns. Calculate 40 turns of the coil, so 40 turns of the coil, and that's number of turns, so that's T, or in some documents they say N. Calculate the MMF and the magnetizing force when a current of 0.5 is applied. 0.5 amp is applied. So that's again very easy. MMF, the formula for MMF is I times T. I is given 0.5, number of turns is 40, and MMF is 20 ampere turns. L for the circumference, the length is the circumference because it's a toroid, it's a ring, and that is pi times D, and D, we converted that 30 millimeter to meter, 0.03. And if you calculate that, L is 0.095 meters. And then the magnetizing force, H, is MMF over L. That's the formula. And we already have the MMF. We found it here, 20. And so 20 over L, we found here 0.095. Calculate that. H is 212.2 ampere turns per meter, and that's as simple as that. These questions are really simple. Number 5 is a little bit lengthy, but it could be easy if you look at it the right way. A component in a switched mode power. A component in a switched mode power supply consists of a coil wound on a toroid core. Determine the following: MMF, flux density, magnetizing force. So we want MMF, flux, which is phi, flux density B, and magnetizing force H. Now I can do this in 2 different ways, and it's given you also the area, cross-sectional area, 60 millimeters squared. So straight away you convert that to meters squared. That is 60 times 10 to the power minus 6. L is given 65, and that is 65 millimeters. Convert that to meters is 0.065 meters. Number of turns is 100. Mu R is 500, and I current is 5 amps. Mu R is relative permeability. That means also that's an indication we will need the other permeability. This is the relative permeability. The absolute permeability is 12.566 times 10 to the power minus 7. That's a fixed value we set for all materials, and we will need that for one of these things that we need to calculate. So there's two ways I can do this. I can either follow this order, find MMF, flux density, magnetizing force, which is making it a little bit long-winded, but we can also find MMF, find the magnetizing force, and then the flux density, and then flux. It doesn't tell you you have to follow this order in the question, so you can do it that way. I'm just going to follow this order first to begin with. This is a little bit, like I said, a long-winded way. Then I'll show you the other way. So that way would be, for MMF is one way anyway, so there's no other ways to find the MMF. MMF is I times T, and that is 5 amps times 100 turns. That's 500 ampere turns. That's that. For the other part, I want to use this method first and then go back to that one again. So for flux is MMF over reluctance. That's the formula again. MMF, magnetomotive force over reluctance. Reluctance itself, we don't have that, so we need to find reluctance. Reluctance itself is L over mu 0 times mu R, or absolute permeability times relative permeability times area. And we have all these, so we can find the reluctance. Reluctance is 65, which is 65 millimeters, so we convert it to meters. 65 times 10 to the power minus 3 for L, the circumference, because it was given in the question. The L is given 65 millimeters. So over mu 0, like we said, it's a fixed value, 12.566 times 10 to the power minus 7, times mu R is 500, times area is 60 times 10 to the power minus 6. Area is given, as you can see, 60 millimeters squared. To convert that to meters squared, you have to say times 10 to the power minus 6. Then you calculate all that, you'll get this value for reluctance, which is amp turn per Weber. Ampere turn per Weber, 1,724,229.4 ampere turns per Weber. And from that, now you put that in this formula, you can find the flux. Flux is, instead of flux, you could just put that symbol phi equals 500 mmf over this value we just found. So the flux is 2.8999 times 10 to the power minus 4 Webers. And then from flux, you can find the flux density. Flux density is phi over A, the cross-sectional area. And so we can say 2.8999 times 10 to the power minus 4 divided by the area is 60 times 10 to the power minus 3. You get the density B equals 4.833 times 10 to the power minus 3 Tesla. And now you can find the magnetizing force. H is I times T over L, or you could say MMF over L, because MMF is I times T. And we already found MMF, which was 500, or you can do it again, I times T over L, 5 times 100 over L, 65 times 10 to the power minus 3, which is again given in the question. The H is 7,692.31 ampere turn per meter. So that's one method. You stick to the order of the question. You just find everything as it is. MMF, flux density, magnetizing force. Now, if I don't stick to the order of this question A, B, C, D, and I want to find it my own way, well, I'll find all of these, and it'll be the same values, but in the order that makes it easier. So we already found the MMF. MMF is I times T, and that was 500 ampere turns. Now H is MMF over L. MMF over L. This is magnetizing force. As you see, the question asks the magnetizing force last. So it's not asking, you're not going to find flux and flux density first. You're finding MMF and then magnetizing force, because it's easier to find that with that first. So that's another method to do it this way. H is MMF over L, and MMF is 500 over L, 0.065, which is that 65 times 10 to the power minus 3. That was given in the question, 65 millimeters. Keep going there just to make sure you understand. So that is that number, and then H is 7,692.3 ampere turn per meter, which is the same as what we found in this method at the end. Yeah, or we found it here right after we found the MMF. And then from that we know the formula for B over H is mu 0 times mu r, or you could say B equals mu 0 times mu r times H, and which is the density basically. We have mu 0, which is a constant value, 12.566 times 10 to the power minus 7, absolute permeability, and mu r is given 500, and H we just found, and we just put the values there, and B is 4.833 times 10 to the power minus 3 Tesla. And then from that we can find phi. Phi of flux is B times A. It's just a transposition for the formula of B. B was phi over A, like we had here, B equals phi over A. Now phi is B times A. We've transposed that to this, and phi is that value B that we found times A. A is given 60 millimeters squared, which is 60 times 10 to the power minus 6 meters square, and phi is 2.8999 times 10 to the power minus 4 Webers, which is the same as what we found in this method. Fine. Then we go to the next question, or the question 6. A coil is wound on a toroid ring core. Determine the current which produces a flux of 1.75 Weber. The HB graph for the core is shown below. So it's given you the area 0.005 meters squared, so it's already meter squared. You don't need to convert it. L is 0.1 meter. Again, there is no conversion needed here. T, the number of turns, is 10 turns. We need to find, it says, determine the current which produces a flux of 1.75. So density, flux density B is phi over A. We've been given the flux 1.75, and we've been given the area, so we can find the flux density B, 350 Tesla. Now we have B, we can find from the graph H. So if B is this one, 350, which is between 300 and 400, that's 350. If you go across here, then you come 350, you come down here, is actually right bang on this, where the curve is just hitting this line. You come down, is 200. So H is 200, where B is 350. So when B is 350, H is 200. So you can write in your assignment from the graph at the flux density of 350 Tesla, the magnetizing force is 200 ampere turn per meter. So H is, you could say, H is 200 ampere turn per meter. And now from that, the formula for MMF is MMF equals H times L. That's just the formula. Because H was also, if the formula for H was MMF over L. And from that also you can find, therefore, you can find by MMF equals H times L. And MMF is 200 times L is given 0.1 meter, so MMF is 20 ampere turns. And also another formula we had was small MMF times MMF, equals I times T. From that, I is MMF over T. Now here's I equals 20 over 10, and I is 2 amps. And that's that. Simple as that. All the questions are answered. Task 2 is to explain what hysteresis loop. That is mentioned in my lesson, so you can just look at that and explain, or do your own research and explain how this is formed. The last question is, using descriptive and technical language, show by sketch and describe the functionality of only 2 of the following devices. So you pick 2 of these devices, DC relay, solenoid, AC motor, DC motor, transformer. I want you to do a little bit of a research, and of course some of these is already answered in the lesson that I've put there, but you can do your own research and find out the functionality of 2 of these. So you pick 2 of these and explain with sketches or diagrams. And if you're using any websites, then you need to reference them, but you need to write them in your own words. You can't just copy and paste. You can copy and paste the pictures and diagrams, but you still need to reference them. But as far as description and explanations of them, you have to write your own words. Read them, understand them, write them in your own words. And also don't forget to write the applications of each one of these. So if you're talking about a DC relay, for instance, and you explain how it works, or a solenoid valve, solenoid, an AC motor, a DC motor, or a transformer, just mention a couple of their applications in real industries as well. All right, thank you very much.